Okay, we've had to talk about permutations, now combinations. The difference with combinations is the actual order is no longer important. Right? So the actual order things happen. So how does that change things? Well, if I'm going to arrange things in a line and the order's not important, well, if I'm going to use all the objects, it then becomes a very trivial question because there's just one way of doing it. They're all in the line because the order doesn't matter. So obviously we're talking about a situation where we don't use all the objects. As far as we're concerned, in a combination, AB would be the same as BA. So obviously visually they're different, but we're more interested in what the objects are rather than the order they appear in. So let's have a look at just some examples to try and get a feel for how we take account of this. If I've got 5 objects and I want to arrange 2 of them. Now, if it was a permutation, there's all the different permutations. We have 5p2, which is 20. But if I'm now saying, look, AB actually is the same as BA and AC is the same as CA, I can get rid of a few of these. Okay? All the ones that are doubled up, we just get rid of. And so that now leaves us with 10. And what it is, it's not that I've just halved it. I've divided by 2 factorial. Again, the number of ways these objects could have been arranged. But because we're now saying that the order they're arranged is not important, we divide by the number of arrangements. So we get 20 divided by 2 factorial, which is 10. Just to show you that idea works, well, 5 objects, arrange 3 of them, a lot. 5p3, that is 60. Now, if I get rid of all the double ups, okay, we got left with 10 again. Okay? Because this time I'm dividing it by 3 factorial, the number of ways I could have arranged those 3 objects. And by coincidence, that also turns out to be 10. All right, so to generalize that, if I've got n objects, I'm going to arrange k of them, not worried about the order. So it's the number of permutations divided by k factorial. Now, if I return that into factorial notation, something interesting happens. We get n factorial on n minus k factorial times k factorial. Look at the 2 numbers on the bottom. I've got n minus k and k, which adds up to give n. So that's what we call a combination. NCK is the notation we have for that one. Okay, 6 numbers chosen from 45. How many ways we can win? That's regular lotto. 45C, 6 different ways. That's a lot of possibilities. 8,145,060 different possibilities of selecting 6 numbers from 45. Incidentally, if you were playing lotto, it's 40 cents a game. So if you were to cover every possibility, it'd cost you 3,258,024. So you'd be guaranteed to win, but it'd cost you a bit of money to do it. Depends what the jackpot is, I suppose. All right, committees. Committees are a combination because all we're interested in is selecting people to go on the committee. Who gets picked first, who gets picked second, doesn't really matter. We're just getting a group of people. So we've got committees of 5 people, and the group that we're pulling from, 7 men, 4 women. How many committees are possible? First of all, again, no restrictions, because that would be the bottom of our fraction in a probability question. Then it will be 11C5, because again, the fact that there's men and women doesn't matter, it's just 11 people we're choosing from. So 11C5, 462 different possible committees. Let's put some restrictions on it. Okay, very sexist. The committee is males only. Males only. Look what happens by being sexist. All of a sudden now there's only 7 C5 committees, because now we're only choosing from 7. 20, what we've gone from 462 possible committees down to 21. That's why those sort of things were silly rules. But then people got enlightened and they said, no. The committee has to contain at least 1 woman. This is where our complementary idea is going to come into account, because at least 1 I could work out, how many committees have 1 women, how many have 2 women, how many have 3 women. But it's a lot easier to say, hang on, I've already worked out how many committees have no women. So I'll just subtract from the total number of committees. And that therefore must leave me with the committees that have at least 1. So that complementary idea again. 462 minus 21, 441 committees. Well, card games. A lot of card games involve 5 cards from a regular pack of cards. The whole basis of poker and who wins poker is based on probability. And obviously the one that has the least probability of happening is the hand that wins. So what's the number of possible hands? 52 cards, as I say. We're going to select 5. The actual order they're dealt in doesn't matter, because if you're a polite card player, you don't pick your cards up until they're all dealt. So it doesn't matter what order they're dealt in. And there we go. We get 2,598,960 possible hands. What's the probability then? So that would be 52C5 will be the bottom, all the possibilities. What's the probability of getting 3 of a kind? Okay, let's look after our restrictions. The first thing we have to choose is which number is going to be the 3 of a kind. So there's 13 different possibilities, and we're going to choose one of them. So we might have decided, okay, it's the 10, or whatever it is. Now, once we've done that, we've got to get 3 of those cards. So there's 4 of them in a deck, so 4C3. So I've got my 3 of a kind, but I now need 2, hang on, oh, my thumb, there you go, 2 other cards. So from 48 remaining cards, because I don't want to get another, well, reality is I'd like to get another 3, but if it's going to be 3 of a kind, I don't want another 3, because then it would become 4 of a kind, not 3 of a kind. So I've only got 48 cards to choose from now. So 48C2, putting that all together, 58,656. So the probability, and it simplifies down, 94 on 2,915. Sometimes with these sort of probabilities, it's easier to express them as percentages, because then people get a feel for the size of the probability. This one's around 3.2%. 3.2%. Don't panic with questions like this, by the way. They can't assume you know what a pack of cards is and how many aces there are and things like that. So you're not going to get a problem like this in an exam unless they were to spell it out to you about all the conditions and explain the whole problem to you. So here's an actual HSC one. We're going to choose a 4-person team from 9 women, 7 men, similar to that committee question we just did, isn't it? How many ways can this team be chosen? So again, it's 16 people, and we're just choosing 4. So 16C4, 1,820. Second part of the question, probability that the team will consist of 4 women. So in other words, the team is all women. So 9C4, because we're only selecting from the women now. So actually very similar to the committee question we just did. So there's our probability. 126 on 1820, which does simplify down to be 9 on 130. There you go. So 10G. Oh, wonder what 19 and 27 are.